Hello and welcome back to Calculus 1, section 2.4 on infinite limits. The goal of this lecture is to see what happens when the answer to the limit is infinity. So you can have limit x goes to some finite value a of f of x, and you get either positive or negative infinity. So that's our goal. Infinite limits. So if you think about the structure of the language used in the title, right? Infinite limit means that the limit is infinity. The answer is infinity. Next lecture will be limits at infinity, which is different wording, and obviously it's going to be a different concept. So infinite limits is referring to this idea that your answer is infinity. Now, we already talked about this case, right, when we said that the function 1 over x, which graphs this way, and you had Juliet from the left and the Romeo from the right. So Juliet said limit x goes to 0 minus of 1 over x was equal to negative infinity. And Romeo was the limit x goes to 0 plus 1 over x equal positive infinity. And then they disagreed, right? Which led us to say there is no limit. So it's a very simple concept. It doesn't take, much thinking to understand what happens here. We also have seen that again for that 1 over x graph that was shifted by 1. I can work out another one of those exercises. So let's say you have limit of 5 over x minus 3 as x goes to 3. And in this case, right, the graph is moved 3 units to the left because it's sorry, to the right because it's minus 3. So if I draw this, I would have to use my pre-calculus knowledge of shifting functions and go over here at 3 and draw my 1 over x. Now, this 5 does stretch a function, yes, but it stretches it vertically and does not impact, left and right. And it's definitely not going to impact this value of the limit, because as you approach from the left, right, so you have the limit x goes to 3 minus of 5 over x minus 3, you are going to get again negative infinity, right? That was the Juliet approach. And then from the right, you're going to go up, and that's going to be limit x goes to 3 plus, which is 5 over x minus 3, and you're going to get positive infinity. So between the two examples, there is no difference. You still have the same example going up and down to make sure that you have right infinities and all of that stuff working. So this is what we have, and we have the now infinities, right, working fine. Now, can we have these infinities? I mean, one infinity, when I say working infinity is working fine, I mean one infinity goes up, one infinity goes down, and you understand, right, that right, they don't match, and you are getting the overall limit to be, I meant to say that the theorem works fine, meaning that the overall limit, right, which was that big theorem, overall limit does not exist. So D and E, and that's it, right, for the overall limit going. So now the theorem works fine, What if we have both of them go the same way? Well, in that case, let's say limit 1 over x squared, x goes to 0, right? So here, that's the graph. So think about this. Think about this for a second. And if you want to tell me, right? If you want to tell me, or you can just wait and then I'll tell you. But you should be able to do the approach on the left, approach on the right. Anyone?
That would be infinity, positive.
Yes. Positive infinity from both sides, right? That's the graphical approach. Positive infinity from both sides, so the answer is just positive infinity. I mean, it's still not a number, right? You can still regard it as limit does not exist because you are not getting 7. But the idea is that, right, the two limits actually agreed in this case, right? So that's also something that is worth mentioning. All right, cool. Now, what is this good for, right? We wouldn't be bothering with this stuff if it, didn't give anything of use. And here is the big title. Vertical asymptotes. So you scratch the surface of this in pre-calculus 1, I believe section 2.6, where your professor said, if you set denominator equal to 0, you are going to find where denominator is 0, which is where the asymptotes exist. And yeah, sure, why not? Except not every one of them is asymptote, and that's the bad part. So professors are very careful to give you examples that don't run into those issues. I mean, some of us might even teach the real deal then, so you don't have to relearn it. But there is only one definition for the vertical asymptote that it's appropriate one, and that is the definition through the infinite limit. So if you remember nothing from that course in terms of vertical asymptotes, that's actually good because you can just learn from scratch, right, the actual definition. So vertical asymptote is a vertical line where, or vertical line at x equals a, where, there we go, limit x goes to a minus of f of x is equal to plus or minus infinity, or limit x goes to a plus f of x is plus minus infinity, or overall limit x goes to a of f of x equals plus minus infinity. This is all you need in your life for vertical asymptote. And this is the first time where I'm going to tell you a little bit about calculus problems and exams and things like that. If the problem says, prove that f of x equals 6 over x minus 2 has a vertical asymptote at x equals to 2, you hopefully see that the answer that the vertical asymptote is at 2 is already in the statement of the problem. The function is in the statement of the problem. And you might say, well, what am I supposed to do here? You already told me, right, that the asymptote is at 2. Yeah, but you are supposed to do the limit to show that you are getting infinity on any of the 3 of these. So your job is to go in and say, oh, this is a shift to the right 2 units. So the graph is going to be shifted 2 units this way. And then if I just do Juliet approach, because I just need one of them to be infinity, these are all or. So I can have one of them or all of them to be, doesn't matter. As long as I have one of them to be infinity, I'm good to go. So let's do the Juliet approach. So limit x approaches 2 minus from the left of 6 over x minus 2. And then you use your eyes and you look at it. And you see it's negative infinity, and you're done. That's it. This is what it means to know the definition, to know the theorem, right? And then to solve the problem using that. Because I gave you the function and I gave you the asymptote. Your job was to verify and confirm or prove that that was the asymptote by using this method of taking the limit. And that's the end of the calculus discussion, right? So your job is to do that. All right, so now we're going to go with another example that would probably get you in trouble if you've seen it in your pre-calculus course. So find vertical asymptotes for f of x is equal to x minus 6 over x squared minus 36. Well, what are the quote-unquote bad points, right? And those are when you set denominator equal to 0. So x squared minus 36 equal to 0. X squared equal to 36. X equal plus minus 6. When you take square root of both sides, you have to have plus minus. So we got 2 points. 2 candidates where you could have asymptotes. Now, most likely in pre-calculus, you would end the problem and you would be wrong because it's not end of the story in case when you have the full definition and full might of calculus in front of you. X equals 6. Check it. Limit x goes to 6 for x minus 6 over x squared minus 36. How do we solve this? Well, we can't plug in 6 because we are getting 0 over 0. So plug-in method is out of the window, which leaves you with algebra. And dare I say clearly, there is only one method, right, that helps here, which is factoring. So limit x goes to 6, x minus 6 over x minus 6x plus 6. These cancel, and you are left with the limit x goes to 6 of 1 over x plus 6, which is now you can plug in, and it's 1 over 12. So this whole calculation here, right, all of this stuff tells you that there is no vertical asymptote at 6. I'll write that in blood. No vertical asymptote at x equals 6. Because on the overall limit, you got 1 over 12. Well, that immediately means that your side limits are also 12 and 12. So, hey, right? It's not a vertical asymptote. So it's not enough for you to set denominator to 0 and get the points. You have to do the limit. These problems are done by the limit. And now we check negative 6. That's going to be the same limit. Now x goes to negative 6, and you still have your same problem. And you solve it the same way. Factor it, cancel it. So limit x goes to negative 6, and now you have your 1 over x plus 6 when you cancel and factor. Well, now when you plug in, you still get 0 in denominator, which means that that method failed. There is nothing else to cancel with algebra, factor, or anything like that. You reach the end of the road, right, for simplifying and all of that stuff. So your other method now is to draw that 1 over x graph shifted 6 units to the left because of plus 6, and use the Romeo-Juliet approach, right? Because the one-sided limits, right, the Romeo and Juliet approach, that always works, right? It's the one that it's the overall limit that runs into this situation when you can't do it. So now, when I draw my function and I draw my 1 over x pieces at negative 6 over here, and I go with, let's say, Juliet over here, going to negative infinity, we are immediately good to go. So limit x approaches negative 6 minus of 1 over x plus 6 is going to give negative infinity, and that is the vertical asymptote. This is enough, 1 of 3. So vertical asymptote at x equals negative 6. That checks out. Now, what was that thing at 6? Because it's still 0 in denominator. Well, when you get a value like this, it means it's the open circle. So if you want to graph this function, you would go like this. You have your x and a y. Then you have at negative 6, you have this, that's negative 6. And at positive 6, let's say here, you just have the open circle like this. So now, there is this one, and then there is this one, gotta hit there, and then go through. This open circle point is 6, 1 over 12. And the other side has the vertical asymptote, VA, at x equals negative 6. So anytime when you do the limit, if it comes out to be a number, value, you have, if it comes out to be the value, you have your open point, right? And if it comes out to be infinity on any of the 3, right, accounts there, you have the vertical asymptote. So from this point on, in calculus and beyond, differential equations, any other math course and high-end physics courses and so on, if you are looking for asymptote, you are doing the limit procedure. You are no longer considering those basic ideas from pre-calc, because as you can see, they do not paint the whole picture. It's not enough to have 0 in denominator, because remember, positive 6 created 0 in denominator, and it did not have vertical asymptote. So you have to be careful and analyze your problems carefully to get this vertical asymptote. And looks like we have plenty of time. I'm just going to mention one more thing now, and we're going to end the course. I mean, not the course, the class. There we go. End the class, and then office hours. If anyone is interested, join at 5:30 at the link posted in announcements in Canvas. All right, so let's talk about this idea of dividing by 0 and getting this infinity in the limit. So we have seen that when you have your 1 over x graph, you can see that as you are approaching, this is now the Romeo approach, as you are approaching 0, so this is x goes to 0, because those are your positive x values, and you are getting smaller and smaller number, walking towards the 0, you see that the y value goes to infinity. So we write this very important limit where the limit of x goes 0 plus of 1 over x is equal to infinity, because that's the approach. Another cool graph that you can keep in mind, also we'll use Romeo approach here, is hopefully you're recognizing this graph as the good old Lnx graph. So Lnx graph, as you are approaching the values from the right, it's again Romeo approach, right? Going this way, x goes to 0. You see that the value goes down to y goes to negative infinity. So in this case, limit of ln x as x goes to 0 plus again, right, is going to give you negative infinity. These values are obtained by looking at the graph, right? The line goes down forever, it's going to be negative infinity, and the line goes up forever is positive infinity. And as you can see, these are your y answers to the x input for the function. So I have the x going towards 0, the y goes negative infinity. Over here also I have x going to 0, and y equals positive infinity in the case on top. So I'm just going to label this one as ln x here as the secondary example. We're going to use this a lot in the class. Chapter 4 will have some graphs. We're going to graph functions by hand and a whole bunch of stuff. So it's very important for you not to lose track of these calculations, and hopefully you'll learn that your calculations here, right, are giving you vertical asymptotes through limit, not through guessing and hoping that, you know, it's there. Cool application, and we're done. It's my favorite example. When you have the outlet in the wall, if you are to short circuit these two on top, they create a mini explosion, and depending on the severity of it and the heat involved, being that all of our houses are mainly made out of wood and cardboard, you can make some real damage. So don't try this at home, right? Now, why is there a small explosion when you short circuit the outlet? Or why is the little spark, which is a really mini explosion, if you are to short circuit the battery with a piece of wire? That's another, right? That's another way of maybe safely doing the experiment. So what happens? The Ohm's law is that the current is equal to voltage over resistance. When you plug something into the unit, it's usually connected to something that it's called a coil on the other side, and that coil has resistance. Then there might be another coil on the other side to induct the voltage for, cell phone charger and blah, blah, blah. But there is a resistance, so this resistance is never zero. So when you have your 110 volts, let's say, and you plug in something that is, let's say, 55 ohms, it works out to be 2 amps on the current. Your fast cell phone chargers are 3.1 amps, right, for fast charging of cell phones and so on. I hope that in this lecture you have seen that if this one tries to go to zero, because let's face it, this graph, when you write 110 over variable resistance that you want to change, is the same as writing y equals 1 over x. There's no difference here. It's the same graph. So the graph for this electrical engineering example here is going to be this puppy, right? Where you have your resistance and you have your current here. Romeo, help us out over here, buddy. As resistance goes to zero, meaning you are short-circuiting this with a piece of wire, your current is trying to be infinite. And that's not bueno. Infinite current is proportional, there is a physics formula, to the temperature. So as current is trying to go to infinity, the temperature is trying to go to infinity in the split second of this short circuit. Therefore, there is a small explosion in there occurring because you're trying to reach infinite temperature instantly, right? And that's what the explosion is. So you have seen the instant use of the theorems and vertical asymptotes and the concept that we just did in this, right? Because when you have nothing plugged in, resistance is infinite. When you plug something that has finite resistance, you get the finite answer. But then if you try to plug in zero, you try to approach zero, then the current tries to be infinite, which makes temperature try to go infinite, and you get little explosion. So there is your application of the lecture we just had. There we go. See you all Wednesday.